Okay, so we're going to be looking at acids and bases. Okay, so when it comes to acids and bases, one of the things that we first think about is pH and pOH. Okay, so for pH is really just the logarithmic calculations of the concentration of hydronium, so H3O, while pOH is the negative logarithmic calculation of the concentration of hydroxide. All right. And so the pH scale, both the pH scale and the pOH scale, runs from the scale from 0 to 14. It's just, depending on what you're looking at, depends if it's acid, base, or neutral. We're more familiar with pH, and so we know that any pH that's less than 7 is typically acidic. If it's greater than 7, it's typically basic. But when we're talking about the pOH, it's actually flipped. And so pOH, if it's less than 7, is basic. If it's greater than 7, then it's acidic. All right, but most cases, you could just live with just looking at the pH scale. All right, just make sure that you know how to go about and calculate pOH if it's ever asked for it. Okay. Um, and so when it comes to acids and bases, one of the first things that we look at and talk about is the ionization of water, all right, or the autoionization of water. And so water could either act like an acid or base. It depends on what it's reacting with. And so if the water is reacting with an acid, all right, then it's going to act like a base. So for example, if we have an acid here, okay, and here's water, then water, this is your acid. Water going to act like a base, and so we know that your conjugates. So we know acids tend to lose a hydrogen ion. Bases tend to gain the hydrogen ion. So here's water now becoming that conjugate acid, and then you have the substance without the H, which is now the conjugate base. Okay, so typically that's what this part is saying. But when water is mixed with a base, all right, then it acts like it acts like an acid. So it's the complete opposite of this. But sometimes water could actually react with itself. Okay, and so this process here we simply call the autoionization of water. Okay, and so when that happens, you have a reaction that looks like this. And I know it's kind of hard to see. I think when I was trying to put the PowerPoint onto this program here, it changed a couple of things here, but so I could just rewrite it for simplicity's sakes. Um, but basically, you will have H2O plus H2O, so two water molecules. All right, and when they hit each other at the right orientation with enough energy, what's going to happen? It will create H3O plus OH minus. So, like if you notice, this is like the acid part of this part, and then here you have the base part. Okay. So this is the autoionization of water, and this typically happens. Okay. Um, and so because of that, because water, when it autoionizes, it produces H3O plus an OH. This reaction is completely reversible. All right, and this is also kind of gives us the pH of pure water. All right, now when you're looking at this, in pure water is always a neutral solution because when we're talking about neutral solution, if you have the same concentration of hydronium as to hydroxide, your solution is neutral, okay? If you have more than one than the other, then it depends, and you may have an acid or base. So, for example, kind of writing this off the side, if the concentration of hydronium is greater than the concentration of hydroxide, here you have yourself an acid. If it's flipped, All right, so the concentration of hydronium is less than the concentration of hydroxide, then you have yourself a base. In all solutions, you always have some level of hydronium hydroxide. It's just about the different levels. But if you have the same concentration, like this one here, of both of them, then you have yourself a neutral concentration, a neutral solution, or a neutral compound, whatever. All right. Um, so for pure water, because for every two water molecules that combines, you create one hydronium and one hydroxide, that there you always have the same number of hydroniums and hydroxides. So pure water will always be neutral. And so it turns out, um, because pH is it's temperature dependent. All right. If you have, if the temperature is at 25 degrees Celsius, the pH is 7. Okay. And so this kind of leads us to what we call the Kw, which is the equilibrium constant of water. And the equilibrium constant of water, in this case, and I'm going to just kind of rewrite it so this kind of makes sense. It's, well, I still used having the highlighted portion. I apologize. Let me write the pin. All right. So it's 1.0 times 10 to the negative 14. All right. So that's that doesn't look right. Times 10 to the negative 14. And this is Kw, and this is only true at 25 degrees Celsius. Okay. Now, if the temperature changes, okay. If the temperature changes, the Kw is going to change as well. And if the Kw changes, the pH will change as well. All right. And so Kw of water is completely dependent, temperature dependent. All right. So autoionization of water is an endothermic process. All right. So as you add heat and temperature into the system, all right, the pH will decrease. All right. The Kw will increase. And as the Kw increases, the pH will decrease. And then if you do the calculation, you'll definitely see that. And I'll show you that a little bit later. Okay. All right. So pH and pOH of strong acids and bases. So this is section 2. Um, so when we're talking about strong acids, they basically dissociate 100%. What does that mean? I mean, I try to give you an example here, but this is not really working out like the way I want it. So what I mean by that is that if you were to add HCl, all right, and you were to dissolve it into water, HCl, being a strong acid, will dissolve completely. All right, so that means it will break up to its prospective ions, and all of it will. So HCl will dissolve into H plus and Cl minus. All right, and that's always the case. So because no acid molecules remains as a whole when you dissolve into water, the concentration of the acid is always equivalent to the concentration of H3O plus ions. And so the pH of an acid could be easily calculated through this equation here. So pH is equal to the negative log of the concentration of H3O plus. And when you think about this, if you think about this reaction here, really what's kind of going on, if you were to dissolve this in water, so let's say you have, well, sorry, HCl plus H2O, what's going to happen is going to happen completely is that HCl being the acid, H2O being the base, the acid is going to donate its proton or donate its hydrogen to the water, and so now water is going to be H3O plus, which is your conjugate base, plus Cl minus. Oh, I took that, messed up on that. This is your conjugate acid, I'm sorry, and Cl minus is your conjugate base. And so when we're talking about pH is basically the logarithmic calculation of the concentration of this. It's really how much of H3O plus you create. All right. And so simply because this breaks up completely, all right? So the amount of this you have will always equal how much H3O plus you create, all right? And so this is the reason why we could use this equation, all right? And so just kind of giving you more of a particulate model of how this works when we're talking about dissolving or dissociating in water. And so before you put it in water, add in water, here's hydrochloric acid. So hydrogen is bonded to chlorine here, and so you see that here, okay, it's bonded to chlorine, and then once it's dissolved into water, if you notice, the bond no longer exists. All right, so they break apart, and so now you have hydrogen ions and chlorine ions. And really, ultimately, what really happens is that these hydrogen ions will actually react with water to create H3O plus. Okay, and so that's essentially what's kind of taking place there. All right, now here's some examples of strong acids. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid, um, perchloric acid, sulfuric acid, nitric acid. Now, for the AP exam, you're going to have to know these by memory. All right, so you're going to have to know your strong acids. These are the only 6 strong acids that we have. And so memorize them. All the other acids you could rightly assume they are weak. All right, so if it's not any of the 6, you could assume that they are weak acids. Okay, and we'll talk about weak acids and weak bases in a different video. Okay, but for the strong ones, these are the 6 strong ones. Make sure you memorize them. Okay, all right. Now, strong bases, same idea. They completely dissociate when you put them in water. So, for example, if we have um, like NaOH, all right, and so NaOH plus H2O, um, what you're going to have, this will completely break up. Actually, we don't even have to add H2O because we understand what's kind of going on here. So as I said, this is going to dissociate. So you have Na plus plus OH minus. So you have more, it produces this OH minus. All right, this is sodium hydroxide breaking up completely once it dissolves into water. Okay. Now, when it comes to strong bases, once just like the strong acids, there's a list of them that you have to memorize. All right, and that list is basically from the periodic table, group 1 and group 2. So group 1 is like the alkali metals, lithium, sodium, those guys. All right, and then the group 2 are your magnesiums, your calciums, your berylliums. Okay, so group 1 and group 2 bases, all right, so as those metals with hydroxides, you could rightfully assume that they're strong bases. Anything else, you could assume that they're weak bases, all right? And so just like strong acids, because they dissociate completely and they make hydroxides when it's in water, you could rightly just easily calculate the pOH, not the pH, but the pOH, which is just a negative log of the concentration of the hydroxide, okay? Simple as that. All right, so when it comes to acids and bases, you're gonna have to make sure you know all these equations, okay? Um, so first, this is your Kw constant, so the very first one. So let's kind of talk about each of these. So the very first one is like your Kw constant, um, where so the concentration of hydronium times the concentration of hydroxide is equal to 1.0 times 10 to the negative 14. All right, and this is the Kw constant. Okay, so the pH, all right, as we know right here, it's just a negative log of the concentration of the hydronium. pOH is a negative log concentration of the hydroxide. And remember, concentration, all right, is always measured in molarity. Okay, with these type of problems that you will see, it's oftentimes they will either tell you, oh, the concentration of hydronium is, or the concentration of hydroxide is, or they either will just tell you a strong acid or a strong base. So you really have to pay attention to the question so you know which of these you're actually really using, okay? The pH plus pOH is always equal to 14. Okay, so if I give you the pH of something and it's asking you for the pOH, just subtract that number from 14. Now, kind of going backwards, if you are given the pH of a substance and is asking for the concentration, all right, of the hydronium concentration, well, the hydronium concentration is equal to 10 to the negative pH. Okay, so 10 to the is the inverse of log. Okay, because it's log base 10. And then same way here, the concentration hydroxide can easily be found from the 10 to the negative pOH. Okay, so one of the things I just kind of want to emphasize is that, especially when it comes to these equations with logs, all right, this tells you that pH is a base 10 of is a calculation of bases of tens, okay? And so to change the pH by 1, all right, the concentration needs to be changed by multiples of tens. So like what I mean by that, like so for example, um, for a pH to equal 1, right, the concentration has to be 0.1. Okay, and so if you do the calculations, you'll see that. So like if we were to plug this back into here, right, we'll see that 1 is equal to negative log of 0.1. That's exactly what this is equal to. All right, if you want the pH to equal to 2, the concentration of the hydronium, all right, is actually 0.01. So here you see what I'm talking about. It's all to the powers of 10, okay? And so if you were to write out this equation, so 2 is equal to negative log of 0.01. And I would suggest that you just plug this into the calculator and you'll see exactly what I'm talking about. So pH is always to the power of tens, all right, of the concentration. So if you want to change it by 1, you got to change the concentration by that power, okay? All right, so let's just go through some example problems. So what I would suggest from this point forward, as you're just kind of reading through this and going through this, um, look at the example problems, pause the video. You don't have to go through the whole video. Attempt the problems, okay? If you're stopped, I will go through each of the questions, all right? So that way you see how I'm coming up with this, what's the thought process, and so on and so forth, okay? So let's look at the very first question. It's asking you, okay, what is the pH of 0.03 molar solution of HCl? All right, so here HCl, what kind of works out is if you write the dissociation of the acid. So we know HCl, all right, it's a strong acid, so it's going to dissociate completely, all right. So it's going to create H plus Cl minus, all right. And really, when we're talking about the pH, you're really looking for this concentration. And because it's going to dissociate completely, whatever this concentration is going to be equal to this concentration. We know that, all right? And so since it's asking for the pH, all right, so we know that the pH is equal to the negative log of the hydronium concentration, okay? And oftentimes, you know, H plus, or I shouldn't put this bracket, is synonymous to H3O plus. It's the same thing, okay? Okay, so anyways, we are looking for the concentration of hydronium. So what's the concentration of hydronium? Just like I said, this is what we're calculating, but this will always be equal to this because it's a strong acid. And so what's the concentration of HCl? Well, it's 0.03. So pH is equal to the negative log, of 0.03 molar. All right. And so once you plug this into the calculator, you'll get your answer. So once you plug into the calculator, you should get that the answer to this problem is 1.52. So that's your pH, okay? And so if you hopefully you look at it, if you look at the pH scale, you can figure out that this is acidic, all right? So this is an acid, all right? Well, also what this means is that the concentration of hydronium is greater than the concentration of hydroxide. Okay, and so that's what makes this an acid. Okay, so that's the question for this one. All right, let's look at example 2. So example 2 says, what is the pH of a 1.3 times 10 to the negative 2 solution of H2SO4? All right. And so it also really helps if, as I said, once again, you write out your equations. So if you write this out, the dissociation of this, so you have H2SO4, all right. When it dissociates, you get 2H plus SO4 negative 2. All right, so there's a couple of things that we need to look at here. Remember, we're looking at the concentration of this, but what do you notice when you look at the mole-mole ratio between this and this? So for every 1 mole of sulfuric acid that dissolves, you make 2H pluses. Remember, pH is the concentration of this. All right. And so what that simply means is that now that we're looking at that, we will have to, since this is the concentration of H2SO4, okay, and for every one H2SO4, we make 2H pluses, then that simply means, all right, and if we do the stoichiometry, I guess, the conversion, is that we see that for every 1.3 times 10 to the negative 2 molar of H2SO4, right, we know that for every 1 molar of molarity of H2SO4, there is 2 molarity of H pluses, all right? And so then that tells us that when we look at this case, then it is, so then you get 2.6 times 10 to the negative 2 molar of H plus. All right. And so this is the concentration of H plus or H3O plus of the hydroniums that you get. All right. And so then kind of going back to what we talked about before. So the pH is equal to negative log of the concentration. So I'm just going to write H plus for this question. The concentration of H plus. Here is our concentration. So we'll just plug this into the calculator accordingly. So pH equals to negative log of 2.6 times 10 to the negative 2. All right. You plug this into the calculator and you should get 1.59. All right. And so that's the pH for this problem. So once again, hopefully you realize that this solution is acidic, all right, because this is a pH that's less than 7, so acidic, and then your hydronium concentration or hydrogen concentration is greater than your hydroxide concentration, okay? All right, so number 3. So it's asking what is the pOH of a 5.2 times 10 to the molar solution of LiOH. All right, so like always, if you notice, the first thing I do, I write out the dissociation equation of each of these strong bases. So LiOH, lithium is a group 1 metal, so I know this is a strong base. So I know that LiOH, when it dissociates, you get Li plus OH minus. So it's a one-to-one relationship, so I could just use these numbers as is. All right. We also know that the pOH is equal to negative log of the concentration of hydroxide. So we're looking at this. And as once again, for every one of LiOH, you make 1 hydroxide. And so these two will equal one another. All right. And so then since we know the concentration of lithium hydroxide, I could simply just plug that into this equation. So pOH is equal to the negative log of 5.2 times 10 to the negative 7. Okay. And then all I have to do is just plug this into the calculator and it will tell us what is the pOH of this solution. So the pOH I get for this solution is 6.28. All right, so what does this mean? All right, well, I could tell you by looking at this, this is the pOH. So the pOH, when you try to figure out if it's an acid or base, is a complete inverse of the pH. So when pOH is less than 7, then this is a basic solution. And what I mean by basic solution, that the concentration of hydroxide is greater than the concentration of hydronium or the concentration of hydrogen. Okay, so that's what this means. All right, let's look at the next question. Next question asks you, okay, so what is the pOH of a 4.25 times 10 to the negative third molar of SROH2 solution? All right, so the first thing we want to do, like always, write out the dissociation of this compound or the solution. So we have strontium hydroxide. So strontium is a group 2 metal. Okay, so we know it's a strong base. It's going to break up completely. So we have strontium plus 2 plus, and then there's 2 hydroxide, so 2OH minus. So once again, remember, pOH, all right, is the concentration of hydroxides that's created, okay? And if you notice, if you look at this, all right, that for every 1 strontium hydroxide that you create, you make 2 hydroxide ions. All right, and so what's going to happen, since this is just the concentration of the strontium hydroxide and the pOH is looking at the concentration of just the hydroxide, you are going to have to multiply this number by the coefficient that it's here. All right, and so the first thing you want to do is multiply 4.25 by 2. As I said, if you kind of want to see the dimension analysis, I'll just go ahead and write that out. Times 10 to the 3 molar of strontium hydroxide. All right, and so we know that for every 1 molar of strontium hydroxide, you have 2 hydroxides, or molarity of hydroxides. And so when you multiply those two numbers together, you get, so the concentration of hydroxide turns out to be 8.5 times 10 to the negative 3. All right, so that's your concentration. Now let's go ahead and find the pOH. And so we know that the pOH is equal to the negative log of, start erasing, of hydroxide. So the negative log of 8.5 times 10 to the negative 3. All right, and then you put this in your calculator and you get, and so you'll get 2.07. All right, and that's your pOH. So once again, so with a pOH of 2.07, remember pOH is the inverse, the exact opposite of pH. So when it comes to able to qualitatively describe if it's an acid or base, in this case it's a base, all right, because in a pOH scale, bases are 7 and under, or less than 7, I should say. And once again, this simply means that the hydroxide concentration is greater than the hydronium concentration. Okay. All right, let's look at the next question, number 5. So number 5 asks you, what is the pH of a 3.53 times 10 to the negative 5th molarity of magnesium hydroxide solution? All right, so let's go ahead and break up this, because this is a base, strong base, because this is a group 2. All right, so we know we have MgOH2, and it will completely dissociate to make Hg plus 2, Mg plus 2, plus 2OH negative. All right, so that's that. All right, so one thing you have to consider when you're looking at this problem, all right, so first of all, this is a base. So if you're going to use any type of logarithmic for a base, you're really looking at the pOH. But this question is asking for the pH. All right, so this is a multi-step problem, okay? And so this probably has a lot that you have to think about, but you need to make sure that you read the question, you understand what is asking you for you to do and what is it giving you, all right? Because you could easily give the wrong answers if you're not paying attention. All right, so first thing that I noticed that there's two hydroxides to every one magnesium hydroxide. So I need to multiply this number by 2. All right. And so when I do that, so my first step, 3.53 times 10 to the negative fifth, and I'm going to multiply this by 2 so that I know what is the real concentration of hydroxide. All right. And so this number is, we have 7.06 times 10 to the negative fifth. So that's our concentration of hydroxide. Okay. Now, with the concentration of hydroxide, what I can actually really figure out is the pOH. All right. And so the pOH is equal to the negative log of the concentration of hydroxide. All right. And so in this case, it's the negative log of 7.06 times 10 to the negative fifth. All right. So when I put this in the calculator, I get a pOH of 4.15. So that's my pOH. Now remember, I talked about this a little bit earlier, is that pH plus pOH is equal to 14. All right. This question is asking you clearly for the pH. What I figured out was the pOH. All right. And so knowing that the pH plus pOH is equal to 14, then I could subtract this number from 14 to figure out what's the pH. All right, and so what you'll get here is that 14 minus 4.15 is equal to 9. You get about 9.85. Okay, and so this is the pH. All right, and that's kind of like your final answer at this point. So, and once again, you really gotta make sure you read the question so you know exactly what you need to do and how to get there. All right. Question number 6. What is the pH or pOH of a 0.02 molar HI solution? All right, so the pH, so we're looking at HI. So we know HI is actually one of your strong acids. So first thing you want to do is kind of write out your dissociation equation of HI. So we know HI breaks up to H plus I minus. All right, and so hopefully one of the things that you quickly notice that this is just a 1-to-1 ratio. All right, so that makes this easy. Also, another thing that you should pick up is asking for the pOH. All right, and so since this is an acid, it is a multi-step process to get from figuring out the concentration of an acid to figure out what is the pOH of that substance. So the first thing that I could do is that I could figure out what's the pH, because I know that's the negative log of the concentration of my acid. All right. And so in this case, it's negative log of 0.02. All right. So when I plug this in the calculator, you get that the pH is equal to I would say about 1.69. All right. And so once again, we know that the pH plus pOH is equal to 14. So if that's the case, then we could say that 14 minus 1.69 will give us the pOH. All right, in which in this case, when we do that, we get somewhere around 12.3. All right, and so that's your answer for this case. All right, next example. Try and straighten this up. Okay, cool. So you have a 10 ml sample of HCl. Solution has a pH of 2.3. How much water must be added to the solution in order to increase the pH by 4.3? Okay, so this is more of like a qualitative questions. I mean, granted, there's some math to this. All right, but there's a couple of things you just have to think about. All right, so you have a 10 mil sample of HCl, okay? And so this sample of HCl gives you this pH, and you're hoping to increase the pH to 4.3, okay? So one of the things that you need to consider is that when the pH is lower, the more the concentration of hydronium that you have, okay? So the greater the concentration of hydronium, the lower the pH, all right? And the inverse is true. The lower the concentration of hydronium, the greater the pH, all right? And so in this case, you're adding water. So essentially, you're really just trying to dilute the solution. Now, the question is, how much can you dilute it by? Well, remember how we talked about earlier that pH um, is a power of 10 calculation. So for you to change the pH by 1, you must change the concentration by a power of 10, and so on and so forth. All right, and so here we're trying to change the pH going from 2.3 to 4.3. So you're changing, so the difference between these two is actually you're trying to change it, or the change of pH is really 2. So if the change of pH is 2, then really, in this case, every time you change a pH of 1, it's 1 power of 10. Well, if you change the pH of 2, it's 2 powers of 10. So, or in a sense, in this case, it's 10 to the second power, or 100. All right. And so in this case, if you want to change um, the pH by 2, then you will need to add about 100 mils of water, all right? Or 2 times of whatever you start off here. So this is 10 mils, all right? And so if you added 10 mils, all right, you change it by pH here. But if you did 10 to square mils, in this case 100 mils, that's 2 pHs. And so that's how much water you will need to add in order to change it by this much. Okay, so let's look at the next question. So here it says a 150 ml sample of NaOH has a pH of 9.5. On a Bunsen burner, 100 ml of water was boiled from the NaOH solution. What is the expected pH of the solution now? All right, so after you evaporated it, um, so okay, so initially you start off with 150 mils. Okay, you subtract off 100 and you get approximately 50 mils. All right. And so in this case, um, when you're kind of looking at it, I think you could kind of game park it where it should be. All right, so you got a more concentrated solution, right? And so you start off with a 9.5. All right, and then so if now you have a more concentrated, more hydroxides than normal, so we expect that the pH will actually increase because there's more hydroxides. So the more hydroxides you have, the um, the greater the pH. All right, so the less hydroxides you have, the smaller the pH. Okay, so you have more hydroxides. All right, and so let's kind of think about this. You have 150 mils. All right, and so remember, pH is always to the power of. Okay, and so to the power of, so we just have to see, okay, how many powers did we kind of decreased by when you think about this? So if we have the decimal point here and we took off 100, all right, if we took off to one of the 10 power, then it would have been about what, maybe 15 mils. Okay. And so if that was the case, if it was just one, then your pH would have been about 10.5. But you did not take off just one of the powers. Really, you just took off somewhere between the 15 and 15.5. And so what you could rightly assume in this case, and this is, as I said, what is the expected pH? It's kind of a ballpark here, that you know that your pH will increase is going to be, it can't be 9.5 because that's your initial, all right, but it may not be as much as 10.5 because for it to be 10.5, you actually had to have only about 15 mils left. All right, so since you have about 50 mils left, I will probably assume that your pH is going to be roughly about 10. All right, roughly. Okay. And so a question like this, it's probably a good idea. You may have to explain yourself a little bit more, but your pH will be around about 10, but it will not be 10.5 because you did not lose a full um, factor of 10, if I should say. Okay. So that's how you will kind of go about with this question. This is actually a really good AP question. Okay, question number 9. This one is interesting. All right, so it says the value of Kw at 30 degrees Celsius is 2.0 times 10 to the negative 14. What is the pH of pure water at 30 degrees Celsius? So remember what we talked about earlier. When you change the temperature, you're changing the Kw. And if you're changing the Kw, you're changing the pH or pOH or whatever the case may be. So it may be a good idea to kind of write out the equation, like I said before. So you have H2O plus H2O. So remember, the Kw of pure water is the autoionization of water. And what you'll get in equilibrium, you have H3O plus OH minus. Now, the thing is, because this is pure water, all right, H3O plus is equal to OH minus. It's the same thing. Remember, for something to be pure, something to be neutral, all right, you have to have the same number of hydronium and as hydroxide. And only works out well this way for water because for every 2 water molecules that reacts, you're only going to make 1 hydronium and 1 hydroxide. It will never be a different number of each, all right? And so, um, since it's Kw, we're talking about in equilibrium, all right? And so at equilibrium, Kw is equal to H3O plus times OH minus, right? And since these two are essentially the same thing, we could call them X, okay? Because we need to figure out what's the concentration of these, okay? So, and since this Kw is equal to, since we have 2 x's, is x squared. All right. And so then we could go ahead and substitute Kw for what we have here. So it's 2.0 times 10 to the negative 14 equals x squared. All right. And so to find x, we will square root 2.0 times 10 to the negative 14. All right. And so this will give us 1.41 times 10 to the negative 7. All right. So x, remember, since we're looking for this, and this is just concentration. So this is your concentration of x. It's the concentration of hydronium. There's also the concentration of hydroxide. All right. So it's the concentration of both. And then so now what you can do at this point, I'm kind of borrowed the space out of here. So then it's the pH is equal to the negative log of the hydronium, which we figured out that it is this. So it's the negative log of 1.41 times 10 to the negative 7. All right. And then when you place this inside the calculator, you'll get roughly 6.85. And so that's your pH. Okay. Yeah, it seems like it's slightly acidic, but when you think about it, once again, you change the temperature, you change your Kw. So at this point, at this temperature, 30 degrees, 6.85 is the pH of water at this point. Okay. Let's look at the next question. Well, which I think is our last question. Oh man, we finally made it. All right, so with this question, we're looking at Kw again. So Kw pure water at 100 degrees Celsius is 5.13 times 10 to the negative 13. Calculate the pH of pure water at this temperature. All right, fine. So same steps like we did last question here. So we know that the water, so autoionization of water, we know that you'll make some H3O plus OH minus. So for every two water molecules, you make one of each, okay? Um, and so when we're talking about from KW purposes, it's just the concentrations of H3O plus times the concentration of OH minus, all right? And so since we're talking about pure water, which pure water is always neutral, we know that the concentration of hydronium is equal to the concentration of hydroxide. All right, and they're equal to one another. And so because of that, we could really just solve for x. They're both the same value. And so in this case, if you were to kind of think about it, kind of going back here, then KW is really just x squared. All right, because each of them are x, each of them are the same value. All right, we know that for sure. All right, so let's substitute KW for what's in this problem here. And so the problem tells us that the KW is 5.13 times 10 to the negative 13 equals x squared. All right, and to solve for x, we have to square root 5.13 times 10 to the negative 13. So this gives us that the x is, so I got 7.16 times 10 to the negative 7. All right, and so that's your concentration of either hydronium or hydroxide. It's one or the other, okay? Since they're both the same thing. So if that's the case, then we could just easily find what pH is. So we know that pH is equal to the negative log of your hydronium in this case. So it's negative log of 7.16 times 10 to the negative 7. You plug this into the calculator and you will get 6.14. And so that's your pH of this water solution at 100 degrees Celsius. All right. So that's these two sections here. As I said, for the example problems, you don't have to watch the whole thing. I would just say maybe just look at the first one, kind of get a feel for it, and then try all the other ones. If you're stumped, then look at those particular problems. If you want to watch this whole video, 48-minute video, go for it. I'm not going to stop you. All right, but if anything else, make sure you go through the first section where I kind of go through the notes and then looking at the example problems and then attempt each of these example problems. All right, till next time.